Well, hello, and we're kind of doing this other thing. I talked to you guys a little bit. I know with having the PowerPoint on behind me, there's some important terms and stuff I want to get to, which is why I have that. I might be a little bit like, the shadows and stuff, you can't necessarily see me, but that's okay. We're going to be talking about some stuff here. Also, you can tell I am at school. That's why I want to use the big whiteboard. Just because of recording on one and like the backgrounds and stuff like that, you're going to see me walk back and forth to the other side of the room. So my voice might kind of go away, and there's actually a point to that a little bit too. But Chapter 8 is about vectors. So if you're in physics class, you're going to be like, vectors, haven't we already mentioned this? We actually have. So it's going to be a little bit of a repeat if you've been in physics class, but you might understand it a little bit more just because of what we've been doing. Usually when I'm in class, I like to talk about Despicable Me just a little bit here because there's a character in Despicable Me, and he talks about vectors. So guys, I didn't really make it a fancy PowerPoint because that way you can be writing as I'm talking. Remember, this is a video, so you can always pause it if you need to. But I have a couple terms here you need to look at and get. Terms. Scalar is a quantity. Quantity is just a number, fancy word for number, having only magnitude. Magnitude is a fancy word for size, okay? So a scalar, like that was 5 times bigger, so-and-so scored 5 times more, 3 times more. It's just a number, all right? Lots of times we have numbers, and in a second I'm going to give you some examples. A vector is a quantity, but it includes both magnitude. Remember, magnitude is a fancy word for size, and direction, okay? So my next slide here, I'm calling on a few people in the class. I just randomly used my spreadsheet. These, remember guys, you can always pause and go back. So if you didn't have enough time to write those down, you can rewind the video just a little bit, pause, and then catch back up. So here are some examples of scalar sentences, I guess you could almost say. Nehemiah ran 5 miles. Chanel walked 6 blocks. Aaliyah drove 35 miles per hour, okay? That would be a speed, or if we were in physics class, I would say that would be a velocity. A velocity can still be considered a vector. So if you notice here, Nehemiah ran 5 miles. Congratulations, Nehemiah. Where did you run? How did you run? Did you just run around a track? Did you run down the street and back? Nehemiah ran 5 miles. It tells us how far he went, but it didn't really tell us where he went, if that makes sense. And there's going to be a couple problems here where we talk about things and we say things, and you're like, well, in all reality, you could have a displacement of 0. And I'm going to talk about that in just a minute, okay? Chanel walked 6 blocks. Maybe she wanted to walk. Maybe right now she needs to get out of the house to go get some food. And so she leaves her house and walks 6 blocks to go to the closest McDonald's or ice cream shop or whatever, just to get out of the house and go somewhere for a little bit. Aaliyah got in her car and must have been driving down the road, and the speed limit hopefully was 35 miles per hour because she was driving 35 miles per hour. Do we know if she was driving towards Pennsylvania, towards Columbus, towards the lake? We don't know where she was going. We just know how fast she was going. So if you notice here, all of these are just numbers. Remember, numbers, just the size. He ran 5 miles. That's just a size. Size is scalar. Magnitude, remember, is our fancy word, but size is that. All right, if you notice, I did click forward on my thing. It changed a little bit, but this part is the same. Again, I'm going to go back and forth. Don't worry, you can pause and things like that. Scalar, vector, scalar, vector. Notice there's just a small difference. Now we know. Nehemiah must have started at his house and ran 5 miles east. Technically probably means he's going to have to run 5 miles west to get back home, and therefore his displacement, if you are in physics class, would be 0 because if he ran 5 one way and 5 the other. And that's what our eventual lesson is going to be today, figuring out what that result was. So Nehemiah ran 5 miles east. Because you see this word east here, it is now a vector. Chanel walked 6 blocks north. It is now a vector because it says north. Aaliyah drove 35 miles per hour south. It is now a vector because it says that. Now, in all reality, Nehemiah, and that's what we're going to get to eventually in our PowerPoint today, Nehemiah maybe didn't just run 5 miles east the whole time. Maybe he ran east and then north and then east and then south and then something else. Maybe his total distance was 5 miles and not necessarily 5 miles east. And that's kind of the difference between a scalar and a vector. Okay, so I know you can't really see me. Maybe if I back up now, you can see me really bright in the spotlight, but that's okay. That's not important. I am going to start like right here. So you know what? I'm going to pick up this marker and I'm going to put a little X, and because I can see the video, I am always going to start in front of the X. So now if we were in class, I would call on somebody and say less than 5, just so you can see me in this screen, and tell me a number. And I'm going to turn towards the hallway, and I'm going to take 3 steps towards the hallway. Okay, and I'm almost off the screen, so maybe we'll have to do less than 3. Right now, am I still at the X? No, that means I have a vector right now because I started at the X and I ended over here. So that would be my displacement again if we were in physics, or if you heard that word or remember that word from Mr. Jabs when you were in physical science. But from that X to me, my vector would be 3, and since I took steps, we're going to be very lax right now and say steps. And I went right, so you could even say right. 3 steps right, that would be my vector. Now, if we wanted to get really challenging, I could start weaving through the room. So usually Jerome sits there, so maybe he's the one who told me 3 steps. So Jamie sits right behind Jerome usually. Maybe I would start at the X again, and I would say, okay, I'm going to call on the next 5 kids. And so Jamie says 2, so I would turn this way and go 1, 2. Trinity says 4, so I go 1, 2, 3, 4. Do you see how I'm going back and forth? Dejanay says 1, so I go 1. Nehemiah says 1, so I go 1. Omarion says 7, so I go 1, 2, 3, 4, 5, 6, and I know I'm off the screen over here for 7. But if you think about it, if I started at the black X right here, and this was sort of 0, and I ended up, I know you can't see me over here, my displacement, even though I went right, left, and I was going back and forth, my displacement would end up being to the right. My final resultant vector would be however many steps I was to the right. So when we are doing vectors, we're going to add everything together. All right, and so I think that's my next screen. You give me just a second here. We're all day today going to be finding what is called our resultant vector. Our resultant vector is a sum of the vectors. That means we have to not only know the number, we also have to know the direction. Okay? So the resultant vector, resultant has a root word of result, which means the answer, right? So the sum of all of our vectors. And please remember, we're just going to add all the vectors. Guys, if I'm going a little bit too fast, remember it's a video. You can pause and finish writing things. So here's the deal. I am going to give us a few simple examples that you guys will have homework like tonight. I call these linear because as I was standing here before when that X was on top of my head and I started to go left and right and left and right, that's just linear because I'm only going in a line. In just a minute, I'm going to do some stuff around the computer as well to give you another idea. But again, I was kind of randomly picking names before, and now I started weaving through the room, but Jamie was the name that came up when I was randomly doing something. So here's your example. Jamie walks 4 miles east, 3 miles west, 8 miles east, then 2 miles east. What is her resultant vector? Now, usually when I start doing this, I say, guys, and that's why I left a little bit of room here, just because I didn't know how close to the bottom of the board I would be getting. I am going to put a little X marks the spot, just like I did for me. And we're going to pretend Jamie starts right inside that box. And then I can just estimate. I suppose if I really wanted to, I could get my ruler out and maybe use inches to represent miles. But I'm going to just think in my head, 4 is bigger than 3, but 8 is bigger. So I'm going to try to estimate these, all right? And let me make sure I have different colors, okay? So I'm going to use black for where she started. And then I'm going to use this. So 4 miles east. East would be towards the right. And so you might want to write a little 4 on that. Again, I'm using colors, but if you don't have colors, it's totally okay. This is just to help us kind of visualize it a little bit as well. Next, I'm doing 3, but guess what direction I have to draw my arrow? And we use arrows a lot because the arrowhead tells us, hey, I was going that way. 3 miles west. Well, you know what? I'm not going to start from where she started. She moved 4 miles. She's now here. It's kind of like she just stopped in space and is hanging out at that spot right there. So from right there, I'm going to draw a line. And I hope you know why I drew that red line a little bit shorter than the blue line. In just a second, I'm going to tell you what we're going to do for that as well. I think you'll know anyway. Next, we're going to do 8. What direction should my 8 go again? Thank you. It should go east, meaning the arrow is going to go in the same direction that I originally went. Now, the only reason I kind of moved up a little bit here is so that we could see. If I want to, since this one's, like, I could go just a little bit up again right here. I'm not going to start at the end of the 4. Because remember, she went 4 this way, then she went 3 this way. And so now I'm going to just go like that. That line should about be, again, we're just approximating, so it's not the biggest deal. But that purple line should be the longest so far because 4 doubled would be 8. So on this line, I'm going to write my 8. And then, oh, guys, sorry, I should have maybe spaced this a little bit better on my PowerPoint, but 2. 2 is still going what way? Now, for this one, since it's not really overlapping or backtracking, I'm just going to put it right on the end of that purple one like that, just because that helps us to see. Now, if I was in class, I would be like, guys, what did she do when she did this 3? And you would say, well, she went back. And lots of times in class, when we think back or the opposite direction, it causes us to want to, very good, subtract. So I'm going to backtrack on my screen 1. Do you see how I put the word add in quotes? Yes, we are going to add all these numbers from Jamie's walk, but since this was the only one that was going the opposite direction, we would probably make 3 in our mind when we do this be negative. So if you would with me, please. 4 is positive, 3 is negative, 8 is positive, 2 is positive, because right now we're pretending east is positive. I suppose some of you, anybody in this class left-handed, I forget for sure. But if anybody in this class were left-handed, sometimes I feel bad for left-handed people. Like I've known quite a few people and they're like, you know, nothing is made for us. Maybe we could pretend west is positive and east is negative. We could. Then this would be a -4, this would be a +3, -8, -2. Our answer would actually be the same. It's just that the negative would actually mean east. So anyway, 4 minus 3 is 1. 1 plus 8 is 9. 9 plus 2 is 11. But here's the deal. If you just write down 11 miles, think about our previous note. Go back a few slides. I'm not going to go backwards on mine right now, but it said Nehemiah walked 5 miles. If you just write 5 miles, you will get this marked wrong. Because right here it says the word vector. Since it says the word vector, guess what we need? Not only the number, magnitude, remember, but I like to use the word size because it helps us out a lot more, but also the, all right, so what way did Jamie end up? Here's where she started. Here is where she ended. Is she 2? By the way, on this one, direction, it looks like our direction is either going to be east or west. Here is where she started. Did she end up towards the east or towards the west? So 11 miles east. All right? So, the next one, you guys all know the little itsy bitsy spider went up the water spout, right? So I kind of use that idea because it's still linear, but it's not left and right linear, it's up and down linear. So I would like you to actually pause the video and try this one on your own. So go ahead and hit pause. All right, thank you for trying this one on your own. I know the words up and down are a little bit confusing. I left a little bit of room over here because once again, if we think about it, okay, here's the roof and here's the water spout where the rain would fall down and stuff like that. Can you see? Good, okay. So you can see that on the side of the screen over here. All right, so here's the little itsy bitsy spider. It's just a little, I put like a little star, and just like I did for Jamie, I'm gonna put a box right there. Now, I have no clue. Maybe my spout needs to be, maybe he was higher up the spout, maybe he was lower, I don't really know. So, the itsy bitsy spider crawled up 5 inches. So again, I could use my colors again, but he went up 5. Uh-oh, the rain must have come, and he pushed him down. Down 8. He tried to crawl back up a little bit again, but then it must have rained some more. All right, what do we know about 5? 5 was up. We should probably say positive. What do we know about 8? 8 was down. We should maybe say negative. What do we know about 2? 2 was up, so that'd probably be positive. What do we know about 6? 6 was down. It was negative. So let's add these numbers. 5, sorry guys, I know that's kind of small off to the side. 5 minus 8 would be negative 3. Negative 3 plus 2 is negative 1. Negative 1 minus 6 is negative 7. But here's the deal. Vectors can never be negative. What did the negative mean to us over here? It's okay if when you did this example you got an answer of negative 7. But negative 7 is not actually the answer. What does the negative mean? Like, look through here. Do any of these numbers say negative? No, we thought 8 down was negative. We thought 8 down was negative. So since 8 down was negative, negative 7, would actually mean that we ended up 7 inches. And again, it looks like our directions on this one were the words up or down. The words up or down. So thank you for trying that one on your own. Hopefully it went okay. Guys, remember, I'm waiting on the Google Meet. If you have any questions, you could be popping back and forth and saying, hey, Ms. Jabs, I'm not sure what's going on. So a couple notes right now. Those first few examples we did were linear. That means I was only going like back and forth. The itsy bitsy spider was only going up and down. We could do something like this. Okay, Ms. Jabs is in the front of the room. Let's see, Madison usually sits in the back corner of the room. You guys know where Madison usually sits? And we're working on something. She raises her hand. I said, Madison, I'll be right there. So you guys can tell I'm in the front of the room up by my board. I've got to take a few steps towards my left. And now I've got to kind of walk down the room. So I'm just going to draw this real quick. Would you agree? I kind of started here, had to walk here, and then I had to walk down the room like that. Well, if you think about that, I started at this X. And here's another thing. When we get to right triangle trig, when we start to go more than one direction, you want to start where you started and end where you ended. Once again, there it is. I drew that in purple just because it was the first marker I saw. But my result, remember how I always started? And I was like, hey guys, we started here. And I would end right here. My resultant vector starts at the beginning and ends at the end. I'm sorry. I thought I put this on there. So where did you start? Okay, you started right up here. Originally I made it a purple X, but then I changed it. Where did you end? So then you would draw that in there. Now, one thing we have to be careful about. We are now going to have to use right triangle trig, probably both Pythagorean's theorem and SOHCAHTOA, to figure out the size of this hypotenuse and then the angle that this is at. And we might have to think about our unit circle because, hey, if we would say that this was a 60-degree angle, that's wrong because 60 degrees, according to this X right here, 60 degrees would be up in quadrant 1. This is not a 60-degree angle because it's in somewhere in quadrant 3. I hope that you can see that's in quadrant 3. Now, depending on, you won't get problems like this today, but we're going to be using right triangle trig. There might be times where before, I think I was talking about Nehemiah again when he went for his run that was 5 miles. He might have ran, like 8 miles this way, 6 miles this way, and he might have made a big old loop. And from the start to the end, his final answer was 5 miles, but he might have run farther than that. It's just the way the right triangle went. Here's what I mean. What if Nehemiah started here? Okay, let me get my different colors so we still know where he started. And he went in like this, then like this, then like this, then like this, and then like that. Maybe he ran this big old zigzaggy route. And that's where he stopped. Well, if he stopped right here, his resultant vector, even though he actually ran, that's red, even though he actually read all those red lines, he ran all those red lines, his resultant vector would just come from that little right triangle that I drew right there. So if we get more than one thing, we want to combine them so that there is only one horizontal. Do you see this one horizontal right here? And one vertical, that would be this right here. So we can use, again, even though he ran all those red lines, we would use the numbers that we would get on those two to make that small right triangle there. Again, that's a little bit maybe of a step up. Our homework tonight is not going to be that tough. So let's look at a few examples here. Trinity ran 4 miles east, then 7 miles north. Find her resultant vector. So, again, right here off to the side, just because, again, we would have room, I'm going to put a little black box right there to say, hey, that's where she started. Ran 4 miles east. Because I already have this arrow going east, I don't need to write east right here. I can just write the number 4. Then 7 miles north. Okay, that one should probably be longer because 7 is bigger than 4. Is there anything else Trinity did? So, where did she start? Sorry guys, I drew that all in black, so I'm going to pick up the blue one now. Where did she start? All right, she started right there. Where did she end? So my answer is going to be the length of that blue hypotenuse and the angle of that blue hypotenuse. Also, where you start is always where you want to consider your origin. So I just put that little plus right there. Here would be 0, 0. Are we in quadrant 1? Since we are in quadrant 1, once I find that angle right there, that would be my final answer. All right, so using Desmos or calculator, honestly, for this first part, you probably could just use your iPhone calculator, but we can't do everything on iPhone calculator because they're kind of a little bit tricky and they're not always the easiest. 4 squared, you might already know what that is in your head too. We're going to do Pythagorean's theorem. Okay, so to do Pythagorean's theorem, we would do 4 squared plus 7 squared equals h squared. And so again, we could do it step by step if we would want to, but we know 4 squared is 16. We know 7 squared is 49. 16 plus 49 is 65. But remember right now that 65 equals h squared. So we would have to take the square root of both sides. So taking the square root of 65, our answer, and here's the deal, we are going to round to the tenths place. Our answer would be 8.1. What unit were we using again? Oh yeah, Trinity was running a certain number of miles. So she ran 8.1 miles. Her resultant vector would be, resultant vector. Can we just say 8.1 miles? What does a vector have to include? All right, so we use Pythagorean's theorem to find the size, but we still have to find the direction. All right? Now, if I look over here, the values I have written in black, we know for sure. When I just found this 8.1, I had to round it. So the blue answer would be rounded, which is okay, because that's what I told you to do. But I am going to use these values of 7 and 4 that are my given values. I know it's 7, I know it's 4. How would you find theta if you, oh, by the way, this was east and north, so this is a right angle. How would you find theta if you had opposite and adjacent? Thank you. So we would write tangent of theta, opposite was 7 over 4. Remember, we're solving for the angle, so remember you have to use that inverse. So you would use tangent inverse of 7 over 4. Now, I would like you to please remember, if you're using a calculator like this, and I know, again, a calculator like this, not a big deal. It's probably already in degree mode. If you are using Desmos, you will have to click on that wrench in the upper corner and change from degree to radian. So if we do tangent inverse of 7 over 4, our answer is a 60-degree angle. And so guys, when we get to this part where we get like triangle stuff, our answer is going to be the number, that is our size, and the direction is going to be an angle, okay? The number that we get is our answer, and then the angle is our direction. So I've got one more example for us to work on, and I even gave us a little hint right here. We have to be a little bit careful about the direction of Madison's resultant vector. All right, it looks like Madison decided to walk instead, and it just looks like she was choosing to use kilometers instead of miles. So that blue X is where Madison started. What did she do first? To west. West is this direction. Since it's 2, my arrow is already telling me that I'm going west, but I'm going to put the number 2 right there. Then 7 kilometers north. Guess what we get? Because west and north are perpendicular. So these 2 lines right here are going to be perpendicular. And that means I would like to find, where did she start? Where did she end? So, once again, we're going to use Pythagorean's theorem. What equation should I write down to find Pythagorean's theorem? Excuse me, to find the hypotenuse using Pythagorean's theorem. Right? We don't know the hypotenuse, so we're still going to have that. 2 squared is 4, 7 squared is 49, 4 plus 49 is 53. So h squared would equal 53. Again, using our calculator to find the square root of 53, we would get approximately 7.3. And again, what unit was Madison using? All right. Now, guys, I don't want you to get too confused for a second. If we look at the triangle that's on the board, I would actually still like to use and find theta right there. I'm still going to use tangent. Most of your homework tonight, you're going to use tangent. When I say tonight, I don't really mean tonight. I mean in the next few minutes. You're going to use tangent to solve that. So let's find tangent of theta. I always like to start out writing tangent. I know I'm going to use the inverse, but tangent of theta would be 7 over 2. So that means to find theta, I would find the tangent inverse of 7 over 2. Sorry, guys, if that's okay. It's still okay on the board. Tangent of theta would be tangent inverse, of 7 over 2. So theta is going to be 74. And guys, don't really worry about what your angle looks like. If it doesn't really look like a 74-degree angle, that is okay. This time, though, guys, I'm not going to write 74 degrees as my answer, because 74 degrees is this angle right here. I'm going to use red just because I think it might show up a little bit better. If this is my origin, and I think about the unit circle, numbers over there would be my numbers between 0 and 90. So here's the deal. What would this blue line that comes straight towards the left be? Would you guys agree that this would be 180 degrees? But this angle right here is forwards or backwards of our unit circle. Are we going the right way or the wrong way on our unit circle? So we're not to 180 degrees yet. We're 74 degrees short of 180. Okay? This would be a point right now if you're like, Miss Jazz, I am not getting this. I am waiting on the Google Meet. Okay? 180 minus 74 is 106. Would you guys all agree if this is where 0 degrees actually is, and I would go from here to here and say this was 106 degrees, and this angle from the resultant vector over here would be 74, 106 plus 74 is 180. So that means my answer, the size is 73, the direction is 106 degrees. And that's how you would find that answer. So linear stuff, I know, guys, is really, really easy. This right triangle stuff is a little bit trickier, but hopefully between all these examples, and I know this video went a little bit longer, but hopefully between all these examples, you'll still have time to kind of get the work done. With the change in how class is going, I want you to have this done before the end of class, which for second period, you guys know what I mean, the second block period is 11:45. So please work on the homework and get it submitted around 11:45. If you need a little bit more time, that's okay. I don't want to go a lot into your next period class. I know there's a lunch break in between, but please be working on this and get it submitted to me, the homework, as soon as possible. Thanks. Hope you guys are doing well. Bye.